All right, lads and ladies, welcome back to Calc 2. I appreciate your patience. I had to polish up some things for my college algebra class. They have the test this Thursday. I had a few urgent issues to deal with there. Today, we are going to continue learning about sequences and series, something I'm very, very excited for us to be doing. We've been talking a lot about sequences. Today, we are going to start talking about series, which is section 11.2. This is going to require coffee, so I'll ask you to give me just 1 second. Oh no, she took all the coffee. All right, damn. Okay, Kitty, come here. No, it's raining. Come on. Inside, baby, inside. Okay. Did she leave any over here? Yeah. All right. This will have to do. So, I mentioned in passing last week that a series is how you integrate a sequence. And I want to show you what I mean by that because there's a really nice analogy with type 1 improper integrals. Before I get into the technical stuff, a word of warning. No kidding. Hey, hey, hey. Listen, I love you too. You can chill. A word of warning. It's very possible to get confused between all of the notation and different concepts. So the things we're talking about today are called series. They're different than sequences. They have their own theorems. They have their own definition of convergence. They have their own notation. And it's all different and it's all specific to series. So I'm going to do my best to introduce this stuff gently, but after a while, it's going to start to feel like there's this massive sea of crazy new notation. And you're going to need to work hard to keep it organized in your brain and make sure you know which notation. Nala, no kitty. No kitty. Why the fuck are you doing that? Sorry. To keep which bit of notation and which bit of mathematics, theorems, results go with which thing. Cannot be trusted. No, you can't. You're just destroying the speakers. You're destroying the chairs. You want to chill here? You want to help me teach some calculus? So, with that warning, here we go. Today we introduce series. And this is section 11.2. Mostly good kitty. Yeah, I ever since we moved into this new house, I've got some nice JBLs, some old JBL speakers from the 70s that are very, very nice. And I resurfaced them a few years ago. But ever since we moved in, she has just been tearing the new screens to pieces. It's a little bit frustrating, but she is a good kitty, so we still love her. I think the first thing we need to do here is talk about the notation. Sigma or summation notation. In theory, you've seen this before, and I should be able to trust that you are comfortable with it. In practice, I know that shit ain't true. Sigma or summation notation is a convenient way of writing a really big addition problem. Convenient or compact way to write big, long addition problems or addition expressions. The symbol, the new symbol is this thing. And if you live in Gainesville, you've probably seen this shit around fraternities and stuff. It's a Greek letter. This is called, it's the capital Greek letter sigma. The lowercase version of this, oh shit, now I forget what lowercase sigma looks like. How, oh yeah, it's like this. It's like that. We're not ever going to use lowercase sigma, but we will use capital sigma. Sigma stands for the word sum, S-U-M, which you know means like to add. So it's a verb, right? To add is a verb. It's the infinitive form, right? Add. So it says add some shit up. Add what up? Sigma of some shit would be read as the sum of shit. And the way that this is used is we put a little index down here to tell us what we're adding the shit up over. So kind of like a definite integral, right? A definite integral says, you know, you're going to take this function and integrate it from here to here. Specifically, and this is where it's going to get confusing because sequences are involved here. If AN is a sequence, we can sum the terms of that sequence with sigma. So let me give you some examples, then we'll look at the general case, and then I'll talk about what it means for these to be infinite in length, and we will have, you know, at that point started talking about infinite series. Example. If I want to sum from n equals 1 to 4, the sequence 1 over n, this is read as the sum of 1 over n taken from n equals 1 to n equals 4. You can think of the top here as saying n equals 4, but we don't usually write it. So what is the sum of 1 over n as n goes from 1 to 4? Well, it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. You see what I'm doing, right? I've got this 1 over n. I'm plugging in all the numbers for n from 1 to 4. And then, because that's what sigma tells me to do, I'm adding all of those up. What is this? I don't know. This is 3/2 plus 1/3 plus 1/4. I'm going to cheat here. I'm lazy. Could have done it by now. As a fraction, please. It's 25 over 12. Okay. Some more examples. If I want to sum from n equals 3 to 6, n squared. This is the sum of n squared from n equals 3 up to n equals 6. This is a number. To figure out what number this is, I write it out in this long form. We're starting at 3. So the first term here is 3 squared. Then the next term is 4 squared. Then the next term is 5 squared. Then the next term is 6 squared. So what is this? This is 9 plus 16 plus 25 plus 36. And again, I'm going to be lazy. 9 plus 16 plus 25 plus 36 is 86. So this adds up to 86. We can go back the other way also. Let me do one more like this. The sum from k equals 0 to 5 of 2k plus 1. So I'm changing the variable. The variable is called the index of summation. We're going to do the same thing. This is the sum of 2k plus 1 taken from k equals 0 up to k equals 5. So I'm going to take 2k plus 1. I'm going to plug in all the numbers from 0 through 5 for k, and I'm going to add up all of those terms. So this is 2 times 0 plus 1 plus 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 plus dot, dot, dot. I'm going to continue this down here, dot, 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 plus 2 times 4 plus 1 plus 2 times 5 plus 1. And that 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. 2 times 4 plus 1 is 9. And 2 times 5 plus 1 is 11. So this is the sum of the first 5 odd numbers, or first 6 odd numbers. So this one I should be able to do. 4 plus 5 is 9. 9 plus 7 is 16. 16 plus 9 is 25. And 25 plus 11 is 34. Hey, I didn't need the calculator. So this one is 34.
25 plus 11 is 36, not 34.
Oh, fuck me. 25 plus 11 is, yeah.
1.
Here I was all proud. Oh, thank you. Thank you. All right. So this is the sigma or summation notation. I'd like us to practice going back in the other direction also, taking something that's written out like this and writing it in the sigma notation. So how can we write the following expression in sigma notation? Let's do a few of these. Let's start with 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1/10. And this is kind of similar to the thing that Alexander was talking about the other day, where you can find like different ways of writing things. Maybe there's more than one way to write this or more than one way to generalize, but you see what's going on here, right? These are the reciprocals of the even numbers that I've added up. Or at least that is the intent.
So it'd be from 1 to 5, or from n equals 1 to n equals 5 of 1 over 2n.
Good. Yeah, if it doesn't jump out right away, you could try to recognize it as 1 over 2 times 1 plus 1 over 2 times 2 plus 1 over 2 times 3 plus 1 over 2 times 4 plus 1 over 2 times 5. So here's like n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. This would be sigma from n equals 1 to 5 of 1 over 2n. What about this?
Powers of 2.
Mm-hmm.
So it's 2 to the 0, 2 to the 1, 2 to the 2. So it's n equals 0 to n equals 6 of 2 to the n.
Very good.
Am I saying that properly? Should I be wording that differently?
Nope, that's perfect. Okay. Are there any questions about how to use this notation or what this means? How to go back and forth from this to this? How to go back and forth from this to this? Can I see? I'm always curious about this. How many people are seeing this for the very first time? Give me a thumbs up react if you're seeing this for the very first time. It's okay. I promise I'm not going to judge. I'm just curious. Okay. All right. So in full generality here, we would say if AN is a sequence, then sigma n from 0 or 1, we'll say 1, up to capital N of AN, this is A1 plus A2 plus A3, all the way out to the very last term would be A sub capital N, all right, the second to last, and the last term. All right, that's what this means. Same thing we've been doing, exact same thing we've been doing. I'm just showing you this in this kind of more general notation. This is the definition of the sigma operator. So you see how people can get confused. There is an interplay between these objects and sequences. We build these things up out of sequences by adding all the terms of a sequence together, or a bunch of the terms from a sequence together, not necessarily all of them, but sometimes all of them. Before I do anything with infinite series, the things we have looked at so far, these are called finite series or finite sums. Before I do anything with infinite sums, I want to talk about the algebra of this sigma operator, because it turns out to have some nice algebraic properties. Yeah. If AN and BN are sequences and K is a constant, then the following are true. Sigma from n equals wherever to wherever, I'll say from 1 to n, of AN plus BN, like this, is the same as sigma from n equals 1 or wherever to capital N or wherever of a little n, plus sigma n equals 1 to cap n of Bn. And sigma from n equals 1 or wherever to capital N or wherever of k times an is equal to k times sigma n from 1 to n. So you got to keep straight the uppercase and lowercase here, right? Uppercase n's and lowercase n's are not interchangeable. They mean something very different. What this theorem says is that sigmas can be split up over addition, and that constant multiples inside of these can pop out. The proof of this is so straightforward, and it's such good practice that I would like you to try to prove it. I'll show you how to get started. To get started, write out each object on the left. So the sum from little n equals 1 up to capital N of a little n plus b little n would be a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus the second to last term here is a(n minus 1 plus b(n minus 1), and the last term is a(n plus bn). I'm a little short on space here. And then you would just reorder it. You'd take all of these guys,
So it's very similar to integrations in this respect.
yeah, the analogy with the integral is deep. It only begins here, but it actually goes much deeper. You'll notice these are the exact same rules as you have for definite integrals. So I could split this up. If I take all the orange stuff, this would be a1 plus a2 plus a3 up to an minus 1 plus an. And then if I take all the blue stuff, that's b1 plus b2 plus b3 out to bn minus 1 plus bn. And I'll let you figure out where to go from here. This is all the orange. This is all the blue. And I'd say, it's up to you to finish this proof, right? I want you to tell me what each of those are equal to. And you can do the same thing with the second piece. If k is a constant, then the sum from little n equals 1 to big N of k times a little n, yes, now we're thinking of plurals, is k a1 plus k a2 plus k a3. Your second to last term here would be k an minus 1, and then your last term is k an. Yeah, the cake is a lie, all that good stuff. We do what we must because we can. You guys know Jonathan Colton is actually on NPR. The guy who wrote that Still Alive song, he's on NPR every weekend. He does the music for the game show Wait, Wait, Don't Tell Me. Funny guy. What could we do to try and simplify this? What do you guys notice about this line here?
You can factor out a k from the whole thing and bring it out to the front.
Yeah, each one of these, you can factor a k. And when I factor a k, what's left is a1 plus a2 plus a3 plus n minus 1 plus an. And I'll let you say where to go from there. All right. So yeah, I didn't actually see who said it, but the coolness here is that this really is the same as the rules for a definite integral, right? The integral from a to b of f of x plus g of x is the same as the integral from a to b of f of x plus the integral from a to b of g of x. And the integral from a to b of a constant times f of x is equal to the constant times the integral from a to b of f of x. So the sequences here are like functions, and the sigmas here are like integrals. And that is an analogy that we will explore more deeply later in section 11.3.
Does this work with exponents? So if I had like n equals 1 to capital N of a sub n squared, is that the same thing as the whole thing squared? With
Sadly,
with,
no.
okay.
This is a good question. I can take a second to address that. So, real quick.
Oh, because it'd be the sum of squares versus the sum of non-squares squared.
Right.
So that's not the same.
Yeah, these two things together tell us that sigma is what's called a linear operator. This is called linearity, or sigma is a linear operator. Other linear operators you've seen, the derivative and the integral are both linear operators. The derivative and the integral both obey this sort of thing. Constant multiples pop out and you can split up over addition. But the integral is also that. What about sigma of an squared summed from 1 to n versus sigma from 1 to n of an all squared? Yeah, you can see if you just take capital N equal to 2, this fails. Shows they aren't equal. Because over here, we would have a1 squared plus a2 squared. And over here, we would have a1 plus a2 squared, which is equal to a1 squared plus 2a1 a2 plus a2 squared. So these are not equal. And we know that that doesn't work with integrals also, right? The integral of f of x all squared is not the same as the integral of f of x times the integral of f of x. We can't just pop powers out of integrals, and we can't pop powers out of sums. So all the rules for integrals work for sums, and pretty much all the shit that doesn't work for integrals doesn't work for sums. That's the good news. So let's see, is there any other preliminary shit like this that we need to talk about before things get fucky? Not really. Not really. So let's do it. All right, what's our goal in section 11.2? We want to understand infinite length addition problems. Sums. That's our goal. So what does it even mean to say add up all the numbers of the form 1 over n squared? Conveniently, in our new notation, we can write down 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... on and on and on forever. I could say that in sigma notation, it makes sense to call this the sum from n equals 1 to infinity of 1 over n squared. But what does that mean? The dot dot dots here, by the way, there's kind of two interpretations. These dot dot dots are called ellipses or c dots in the LaTeX notation. If after some time, after these dot dot dots, you have another term, that means this is a finite length sum that is just very long. But if you've got dot dot dots like a plus and dot dot dots like this, and then nothing afterwards, that is our way of saying goes on forever. Following that pattern. That's just what the symbols mean. So the next term would be 1 over 5 squared and 1 over 6 squared and 1 over 7 squared. I want to know if you add up all of those for every positive integer n, what do you get? Well, it would make sense to call it this, right? Because if you were to start writing this out and just never ever stop and keep going, you would get this. But what the fuck does that even mean? And this is the first place I would like to appeal to the similarity with the integral. Recall that the integral from 1 to infinity of f of x dx is defined as lim r to infinity integral 1 to r f of x dx. So maybe we should define the sum n equals 1 to infinity of a n to be, we use r here for real number. I'm going to use n here for natural number, capital N to infinity, sigma n, little n from 1 to capital N of an. Analogously, and we do. That's precisely what we do. You guys with me on this? All right. So we're ready to do it then. I'm going to write down the definition of an infinite series.
Wait, can you go back for a second, please? I'll take
Yes.
a picture of that. Got it, thank you.
I'll hold here just for a second in case anybody else is still writing. So kind of, okay, I'm going to define this thing to be the limit of this thing. Just like I defined this integral to be the limit of these smaller integrals, right? Infinite sum, limit of finite sums, infinite integral, limit of finite integrals. Back in improper integral land, this was cool because I knew what to do with these things, right? I know how to do definite integrals. I know how to find a formula We have the fundamental theorem of calculus that says, okay, find an antiderivative for f and plug in these numbers, and that will give you a formula for this, which you can then take the limit of. Bad news, there isn't anything like that for these. There's only a few very special cases where you'll be able to find a formula for this. The sequence here is playing the same role that f of x plays in the integral. It wouldn't be correct to say that the sequence is f of x, but the same thing that f of x is doing here, the sequence is doing here. It's being added up. So this is just an analogy. It's an analogy. They're not equal. This thing is not equal to this thing. And these are certainly not equal to each other. It's just an analogy. But it's a powerful analogy. This is what I meant when I said series are how we integrate sequences.
Will little n never always be an integer, or will it ever be like a fraction or something?
Always integers. Yeah, always non-negative integers. 0, 1, 2, 3, 4, 5. Always integers.
It can't be negative?
For us, we're not interested in negative integers. There are things called bilateral series that run from negative infinity to infinity, but we won't be messing with those. So we're ready to do this thing. Let's do it. Given a sequence an, and I'll say that this sequence starts at 0, right? Given a sequence, we can define the infinite series, which is the sum of all the terms of the sequence as sigma n from 1 to infinity of an. This is the thing I want to define, but it's got problems. It's not entirely obvious. How do I add up infinitely many things? That's the obvious problem here. My little hand will get very, very tired before I write out and add up all of those infinitely many things. We define this to be the limit as capital N goes to infinity of the finite sum, sigma n from 1 to capital N of an. Period. The finite sum, sigma little n from 1 to capital N of an, is called the partial sum of the series sigma n equals 1 to infinity of an. These partial sums actually form a sequence. That's what I mean when I say it's a little confusing. Of their own. So we denote them as, I will always use a capital N here to try and make life less confusing. Your book fucks up the notation and uses a lowercase n here, which is very, very confusing. I am going to try to make this tolerable.
What does it say after so we? Devote? Oh, never mind. Yeah.
denote. Denote, write them. So Sn is the nth partial sum. It's the partial sum of length n. S1 is just A1. S2 is the sum of length 2, A1 plus A2. S3 is the sum of length 3, A1 plus A2 plus A3, and so on. And in general, Sn is A1 plus A2 plus A3 all the way out to An, which you recall from earlier is the long way of writing this sigma notation thing. This is an An. All right. This is how we define an infinite series. It is the limit as n goes to infinity of the nth partial sum. So the full infinite series, sigma n from 1 or wherever up to infinity of an. This is the limit as capital N goes to infinity of sigma little n from 1 to capital N of an. And we can write that just as limit capital N goes to infinity of S sub capital N. The funny thing is that Sn, S sub capital N is a sequence. There's a first one, a second one, a third one, a fourth one, an nth one. The way we define convergence for an infinite series is in terms of its sequence of partial sums. If the sequence of partial sums is a convergent sequence, then the infinite series is a convergent series. And the sequence an converging doesn't tell me whether the sequence Sn converges. All right. I'm going to hold here for a second in case there are any pieces you need to write down. I'll say up here for a second. Actually, I'll do this in two pieces. We'll zoom in a little here. Kind of everything up to here. Everything up to here. Screenshot if you want it. Move it in a few seconds. And then everything below here. Definition. We say the infinite series, sigma n from 1 or wherever to infinity of an, converges if its sequence of partial sums, which are the Sn's, is a convergent sequence. Are you okay? If the sequence of partial sums Sn diverges, we say the series sigma n from 1 to infinity of an diverges. This is what it means to say an infinite series is convergent or divergent. It's all about the partial sums. And you can see how there's room to get confused between convergent series and convergent sequences, because the convergence of a series, this is a series, depends on whether its sequence of partial sums is a convergent sequence. So I think this is enough of the abstract. We should look at some concrete examples. Are you guys ready? Okay. The simplest examples out there are geometric. So let me start it at 1. 1 to infinity, 1/2 to the n converges or diverges by investigating its sequence of partial sums. Sn. So I originally wrote start at n equals 0. I want to start it at n equals 1. It'll just these first few examples, it'll be easier. First, the full series, just to make sure we know what we're talking about, the sum from n equals 1 to infinity of 1/2 to the n is 1/2 to the 1 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4, and so on and on and on forever. This would be 1/2 plus 1/4 plus 1/8 plus 1/16, on and on forever. Because it goes on and on forever, I can't just write it out and add them up. It's too much shit. It goes on for too long. That's the whole issue with infinite series. When you write them out like this, they're too long to compute. So instead, I figure out the sequence of partial sums. I'm just going to write out the first few terms of the sequence of partial sums, S1. S1 is just 1/2 to the 1, which is 1/2. What is S2?
1/4.
Careful, A2 is 1/4. S2 is the sum of length 2.
So it's 1/4 plus 1/2.
Yeah, it's the first two terms of the sum. Oh shit, 1/2 to the 1 plus 1/2 to the 2. Or yeah, 1/2 plus 1/4, which is what? 1/2 is 2/4, so this is 3/4. Okay, what about S3? This would be 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3, right? S3 is the sum of length 3. It's the third partial sum, which is 1/2 plus 1/4 plus 1/8. And if you add all of those up, you'll get 7/8. S4 is the sum of length 4. That's 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4, which is 1/2 plus 1/4 plus 1/8 plus 1/16, which is 7/8 plus 1/16, which is 14/16 plus 1/16 is 15/16. And just from these first few, I think we might have a guess at what Sn is. Does anybody see a pattern? 1/2, 3/4, 7/8, 15/16.
Getting really close to 1.
Yeah, but let's be more precise. What is our guess at the formula for the nth partial sum?
Is it
N
2 to the
minus
power
1
of n minus 1 over 2n? 2 to the power of n, I mean?
Yeah, Lydia's got it exactly. The downstairs is always 2 to the n. And that makes sense because we're adding up a bunch of fractions whose denominators are powers of 2, ending at 2 to the n. So when you have a common denominator, 2 to the capital N, that's going to be that denominator. Like 16 is 2 to the 4, 8 is 2 to the 3, 4 is 2 to the 2. Upstairs, the numerator is just 1 less. So this is 2 to the n minus 1. And this is correct. You can calculate S5, S6, S7. This is correct. So we know that in general, the sum from 1 to infinity of an is the limit as capital N goes to infinity of Sn. Therefore, the sum from n equals 1 to infinity of 1/2 to the n should be the limit as capital N goes to infinity of 2 to the n minus 1 over 2 to the n, like this. You guys with me on this? Now this limit, this is actually not hard to calculate. This is limit capital N to infinity 2 to the n over 2 to the n minus 1 over 2 to the n. I'll write it out. And 2 to the n over 2 to the n is 1. And without the limit, just algebraically, you can cancel those and get a 1. So this is 1 minus 1 over 2 to the n, like that. As capital N goes to infinity, what does the 2 to the n down here do?
it gets very, very small.
So the 2 to the n itself is going to go to infinity. And 1 over infinity, that's going to get very, very small. This is 1 minus 0, or just 1. This leads to one of the worst math jokes I know. Are you ready? An infinite number of mathematicians walk into a bar. The first one says, "I'll take a beer." The second one says, "I'll take half a beer." The third one says, "I'll take a fourth of a beer," and so on. The bartender says, fuck, I hate you guys, and just pours 2 beers. All right. I'm sorry. It's not the worst math joke I know. There are worse. There are. We'll get there.
Have you told that joke in a classroom setting?
Yeah.
Have you gotten similar reactions?
Precisely the reaction I got here. Nobody laughs. But I just can't help it. You know, it's just one of those things. I apologize
Yeah, you
in advance
continue.
for the remaining bad jokes. You know. So the infinite sum here, if you add up infinitely many things, 1/2 plus 1/4 plus 1/8 plus 1/6, on and on forever, you get 1. Yeah, yep. That's the thing. I wrote a capital N here. This should be a little n. I'm so sorry. I just noticed that. Yeah, this is a little n. Sigma n from 1 to infinity, 1/2 to the little n. That's equal to this. So sorry. So yeah, if you add up all of the powers of 1/2, those add to 1. There's a reason these are called geometric, by the way. You want another bad math joke? What's purple in commutes? An abelian grape. What's a yellow complete normed linear? A Bananock space. They're bad. They're bad. I got lots of these. They're all really bad. The reason this is called geometric is because if you take a square with side lengths 1 and you begin chopping it up, this piece now has area 1/2, right? And you continue chopping it up, each time bisecting what you have. This piece has area 1/4 now. Continue chopping it up. This piece has area 1/8 now. Continue chopping it up. This piece has area 1/16 now. Continue chopping it up. This piece has area 1/32 now. The total area here is 1. We know that, length times width, right? But it's also 1/2 plus 1/4 plus 1/16 plus 1/8 plus 1/32, and so on. This is how these were done back in, I think the Greeks knew this shit. Definitely in ancient India, they were all over this shit, had no problems with it. And in ancient China, geometric series were well understood. Certainly during the Islamic Revolution in the Middle East, they were well beyond this. They knew this and quite a bit more. And this is why we call them geometric. There is, yeah, so if you start trying to draw tangential lines here at each of these, you can arrive at something that looks kind of golden spiral-y. The way I did this, I'm cascading down into the bottom right corner, but if you always choose to try to bring it into the middle, you can get something that is kind of like the phi golden ratio golden spiral thing. But I'm not going to go there. That's a whole different topic. What I do want to do now is show you what geometric series look like in general. So you remember what geometric sequences are. If it can be written as an equals a0 times r to the n. This is how I showed it to you in class. Your book uses a slightly different notation because they always assume n starts at 1, so they have an n-1 here, and I don't think they put the 0 subscript here. But doing it like this makes it pretty. Just works a shitload better. a geometric series is a series formed out of a geometric sequence. That is a series of the form sigma n from 0 to infinity a naught times r to the n. And here a naught and r are constants, right? I'm going to go ahead and call this thing S. And that's something you'll see me do often. Right, so Sn is the partial sum for the full series. It's nice to just call the full series S.
Do you put the lines on the S so we always want a 5?
Yeah, to make sure that it's not confused with a 5. Yeah,
I appreciate that. Thank you.
of course. So what I'd like to do now is give you the full convergence result for geometric series. Let me see if I have time. 12:15, 12:30, right? 1:45. It's going to be a little tight. We're going to go a little bit over. I apologize, but let me give you the theorem. Geometric series sigma a naught r to the n. I'll leave off the indices here when the thing I'm saying applies to them regardless of where they begin. Maybe for now, I won't do this to you yet. N equals 0 to infinity r to the n. Converge if the absolute value of r is strictly less than 1 and diverge otherwise. In the event that they converge, if a geometric series converges, the value of its sum will be, remember it like this, the starting term divided by 1 minus the common ratio. Sometimes, like in the example above, that will be a naught over 1 minus r. This is if a naught is the starting term. But if my series started at 2 or 3 instead of at 0, then the starting term wouldn't just be the constant a naught. I should say only if a naught is the starting term. The book gives you this formula, and it's this which I'm going to prove. But this is how you should remember it. Because there are a lot more cases. A lot of series don't start at 0, like the one we looked at a second ago starts at 1. And if I use this formula on that problem, I'd get fucked unless I used it in this form. All right. This is your first big result on series. So your convergence results for series page in your notes should have 2 things at this point, maybe 3. Should have the definition of an infinite series, should have the definition of convergence for an infinite series, right? And should have this. I'm going to go ahead and prove this for you. You don't put the proof on that page, just put the theorem. Specifically, both forms of this formula, and that these converge if and only if r is smaller than 1. Smaller than 1 meaning has absolute value less than 1. Proof. Sigma n from 0 to infinity, a naught times r to the n. I can pull out the constant a naught, and I get here sigma n from 0 to infinity, r to the n, which is by definition a naught times the limit as capital N goes to infinity, sigma n equals 0 to capital N, r to the little n. This is equal to a naught times, oh shit, down, equal to a naught lim n to infinity. I'm just going to write out what this sum is. It's 1 plus r squared plus r cubed. Second to last term is r to the capital N minus 1. Last term is r to the capital N. So what I need to do, I need to find a nice formula for 1 plus r squared plus r cubed, r to the n minus 1, r to the n. So we're going to hold here for a second. I'll call this line star. My goal is to find a nice formula for the bracketed expression, one that I can take the limit of without too much hassle. I'm going to do that. I'm going to find a formula for this and then come back and plug it in here. To that end, I will look at, I know this is weird, 1 minus r times 1 plus r squared plus r cubed plus dot 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 plus r to the n minus 1 plus r to the n. The question in your mind should be, why the fuck would I look at that? And I'm saying, because it does something nice, just trust me. If you distribute this 1 minus r, this is 1 times that series. This is r squared, r cubed, r to the n minus 1, r to the n, minus r times 1 plus r squared plus r cubed plus r to the n minus 1 plus r to the n. All right, if you have to go, you have to go, but please watch this. It's a fun proof. It's very cool. So first I split this up as 1 times the bracketed expression minus r times the bracketed expression. I'm distributing this. Now within each of those, I'm going to distribute. If I distribute the 1, I just get this thing. If I distribute the r, all the powers go up by 1. So this becomes 1 plus r squared plus r cubed plus dot 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 plus r to the n minus 1 plus r to the n. And now I'm going to distribute the negative r. I'll get minus r, right? Negative r times 1 minus r squared, negative r times r, minus r cubed, negative r times r squared, minus r to the 4, plus dot dot dot, r negative r times r to the n minus 1, sorry, minus dot dot dot, minus r to the n minus r to the n plus 1. So I distribute the 1 here. I just get another copy of that thing. I distribute the minus r here. And I get this. Negative r times 1 is negative r. Negative r times r is negative r squared. Negative r times r cubed is negative r to the 4, and so on. So the 1 here survives. But then I have plus r minus r, plus r squared minus r squared, plus r cubed minus r cubed. The next term inside this dot dot dots is a plus r to the 4. And here I have a minus r to the 4. I've got a plus r to the n minus 1 here. The term right before this inside the dot dot dots is a minus r to the n, or minus r to the n minus 1. And then I've got a plus r to the n here, minus r to the n here. So the only things that survive this process are 1 and minus r to the n plus 1. That's why we multiply by 1 minus r, because a bunch of shit goes away. In particular, there's only 2 terms that survive. No matter how long this original sum was, when you multiply by 1 minus r, only these 2 terms survive. So what this means is that 1 plus r, that bracketed expression, plus r squared plus r cubed plus r to the n minus 1 plus r to the n. If you divide over, you get that this is equal to 1 minus r to the n plus 1 divided by 1 minus r. And plugging this back into star, that yields sigma n from 0 to infinity a naught r to the n equals a naught times limit n to infinity this thing, which is this thing, 1 minus r to the n plus 1 over 1 minus r. And that is equal to, there's only one place where n shows up anywhere in this expression. This is a naught times 1 minus the limit as n goes to infinity, r to the n plus 1, all divided by 1 minus r. And this is something we have a theorem about. That's the same as a naught times 1 minus r times the limit as n goes to infinity of r to the n all over 1 minus r. So what am I doing? I'm pulling an r out here, right? R to the n plus 1 is r times r to the n. That r can come out like this. And this limit, recall, lim n to infinity r to the n. We had a theorem about this from last week. It's equal to 0 if the absolute value of r is less than 1. It's equal to 1 if r is equal to 1. It's DNE if r is less than -1, and it's plus infinity if r is greater than 1. If r is equal to 1, this whole expression is in real fucking trouble because the bottom is 0. If r is smaller than -1 or bigger than +1, then this limit doesn't exist. So at this stage, we get a0 times 1 minus 0 over 1 minus r, but only if the absolute value of r is less than 1. Otherwise, the expression has shitty limit. That's if the absolute value of r is strictly bigger than 1 or is undefined. That's if r is equal to 1. And this is a0 times 1 over 1 minus r, or if you like, the way the book writes it, a0 over 1 minus r, as promised. And that's the proof. So your geometric series, sigma n from 0 to infinity, a0 times r to the n, will have a finite value, but only if the absolute value of r is strictly less than 1. Otherwise, this thing fails to exist. The limit will either be infinity or DNE. In the case where r is equal to 1, what you're really doing is adding up a bunch of constants here. It's a0 plus a0 plus a0 plus a0 plus a0 plus a0 infinitely many times, which doesn't give us anything. It's obviously infinity. But I will come back on Thursday and pick it up here. On Thursday, we are going to look at a lot more geometric series. I'll go back over this result. I'm not going to go back through the proof, but I'll go back over this result. And then we'll look at a bunch of specific examples involving geometric series. And then I will show you one other kind of series that is very important called a telescoping series. And we'll develop a few theorems as well. There are a couple important theorems that you guys need to learn. And that's when you guys are going to be turned loose for spring break. Oh yeah, we did talk about that. Yeah, let's look at the Discord setup. I'll go ahead and do that right now. Or has anybody else made a Discord or brought me or anything like that for this class? All right, I have not set it up, but I'll go ahead and do it now and post it to I'll go ahead and set up a server and I will post it in, do I have it on here? No, okay, I gotta use it in the browser. The cake is indeed a lie, but Jonathan Colton is pretty cool. Also, if you haven't played it yet, Cyberpunk has a cute reference to Portal. I won't spoil it for you, but do the missions for Delamain if you play Cyberpunk. All right, take care, guys. Have a good afternoon. Work hard. There's a new homework that's going to drop in just a little bit. Take a look at the first few problems there, and then I'll see you all on Thursday. Bye.
Thank you, Professor.